So what do we know? The initial ionization of the clouds will become, the initial ionization takes place because of friction among ice particles. We don't understand what causes further separation of the charges. We don't understand why the top of the clouds become positively charged, the bottom negatively charged. We know that the Earth is initially negatively charged. Somehow, magically, it becomes positively charged just before the lightning. All right, so speaking of separation of charges. Oh my God, this thing is working finally. Let's talk about something being positively charged, negatively charged, and neutral. Okay, so let's get back to the concept of net charge. What is net charge? Net charge is the sum total of all the charges that we're looking at. All right, so in this case, what is the net charge if I place a positive charge here? Okay, so now it's going to be -3, right? What's the net charge right now? It's going to be -2. What is the net charge? It's going to be -1. What's the net charge? It's going to be neutral. So now it's got equal number of positive and negative charges. What is the net charge now? It's got 5 positive charges and 4 negative charges, so now it's positive charge. Okay, so things can be positive charge, negative charge, as well as neutral. So you can charge something up positively, you can charge something up negatively, and also things can be neutral. So these are just insulators, right? What's the difference between an insulator and a conductor on the atomic scale? Right, so you guys are saying that the metals are good conductors and something about the free electrons. So what do you mean by the free electrons? For now. All right, well, what I'm looking for is what's the difference between a conductor and an insulator on the atomic scale? Why is it that the conductors are able to conduct electricity, whatever the hell that is, and the insulators are like, okay, it's a stop sign, nothing is going through. All right, so let's get back to the concept. All right, so you guys can see the PowerPoint. So you guys are looking at the sodium atom. It's got 11 positive charges at the center. You got 11 negative charges moving about the center. So the net charge is going to be 0. So this is neutral. All right, so what would happen if you were to get rid of the outside charge? All right, so now it's got 11 positive charges and 10 negative charges. So this becomes positive charge, positive ion. So which means that the sodium is going to have a tendency to become positive charge in chemical reactions. You're looking at the fluorine atom. It's got non-positive charges and negative charges. So the net charge is neutral. It's all atoms will have equal number of positive and negative charges. Now, what would happen if you could just magically place a negative charge here? All right, so now it's going to have 10 negative charges and non-positive charges, so it's going to become negatively charged. So things could be positively or negatively charged, obviously, depending upon if they have more or less electrons. So the question is, why is that conductors are good at conducting and the insulators are not? I guess it goes back to, the simple explanation is from classical physics, is going to be related to something called the octet rule. Those of you guys who've taken chemistry, you would probably remember what the octet rule is. Okay, so what is the octet rule?
Electrons are happy if they have 8 or like 8 or 16 on the outside.
Okay, so octet means 8.
8 electrons.
Okay, I'll give you 5 points for that one. Guys, octet means 8, so we will use the 8 rule. All right, this is classical physics. A lot of the physics is made up. This is your Disney reality. A lot of what I'm about to say is not going to hold water when you get to modern physics, okay, including the structure of the atom. All right, so octet rule is the 8 rule. According to chemistry, the atoms, the elements will get into chemical reactions in order to complete their outermost shells with 8 electrons. All right, so this is what drives chemistry. Any and every single element is going to get into chemical reactions in order to complete their valence shells with 8 electrons. All right, so here's a situation that we're looking at right now. Notice that we got 2 atoms right next to each other, and octet rule is unsatisfied. All right, in the outermost shell, the valence shell, this got 4 and this got 4. All right, so they want 8, but they got 4. So what do? Ideally, they like to complete the outermost shell with 8 electrons. It's not happening. And both of them got 4, and both of them will need 4 more electrons. So what do? What they do is they will electron share. All right, so in the outermost shells, the electrons will jump from one atom to the next one. These are known as the conduction electrons, so they are free to move. When the octet rule is unsatisfied, when they have enough electrons in the outermost shell, I'm talking about the atoms, they do share these electrons. These electrons are going to be free to move from one atom to next atom. All right, so these are known as the conduction electrons, and the outermost shell is known as the valence shell. All right, so this is a made-up explanation from classical physics. So the octet rule is the tendency of the atoms to complete their valence shells up to 8 electrons. So that's what we're dealing with. Now the insulator. Oh, this one is 100% made up. I know it's 100% made up because I'm the one who made it up. I even said, hey, here's your Disney reality. So whatever the hell you guys use, don't memorize it. All right, so I'm going to give you an atomic structure, and then I'll make sure that the outermost shell is complete with 8 electrons. So the octet rule is satisfied. And then I'm going to call this material plastic. It's not. This is a noble gas. And somehow I'm going to go in there, and I'm just going to, through friction, I'm going to deposit some negative charges all over the place. Notice that these negative charges will not be able to attach themselves to any of the atoms, right? Because the octet rule is satisfied. Okay, so the insulators kind of work on this principle. When the octet rule is satisfied, the free electrons, when dropped, they got no place to go. When the octet rule is not satisfied, electrons are free to jump from atom to atom. They become conduction electrons. Okay, so that's the simplistic explanation that we will get to use from classical physics. All right, so conductors, octet rule is not satisfied. Valence shell electrons are being shared, which means that they're free to jump from atom to atom. The insulator's octet rule is satisfied. Free electrons are not able to attach themselves to any of the atoms, so they got no place to go. For white,
on an insulator, an electric charge stays where it is. But on a metal, it spreads out instantly. That is, the metal conducts electricity. On a deeper level, this is what happens. Each atom of a metal can be thought of as a positive ion with one or two loosely bound outer electrons. When two metallic atoms are very close together, the outermost electrons can pass easily from one to the next. As more atoms are added, electrons can range farther afield. Those mobile electrons are known as conduction electrons, and they give metals their special properties. In this way, all metals are electric conductors because every metal is like a giant molecule in which a number of electrons are shared equally by all the atoms. Picture it as a structure of positively charged ions, glued together by a fluid of mobile electrons.
Okay, let me answer this question.
As more the outermost those mobile electrons are known as conduction electrons because every metal is like a giant molecule.
Focus on physics. This comb is negatively charged. Does this mean that water is positively charged? Yes or no?
Yes.
Comb is negatively charged. Does this mean that water is positively charged? All right, let's test this. So when I was in graduate school, my dad was visiting. My dad is a medical doctor. He loves physics for whatever reason. He also thinks that he's good at it. I don't know why he has that kind of weird confidence because I don't think he is. So he said, Ken, do you know water is positively charged? I said, Dad, it's not. He said, yeah, it is. I said, Dad, it's not. He said, let me prove it to you. I said, go right ahead. So the next thing you know, he's doing this demonstration. So I'm watching it. He said, the comb is negatively charged, right? I said, yes, it is. And the opposites attract, right? I said, absolutely. So that means that the water is positively charged, right? I said, absolutely not. I said, Dad, we could do the same experiment a little bit differently. I said, just charge up the comb once again.
Hold the comb near the paper.
And then let's stop at this point. This is cute. All right, guys, paper, is it positive charge, negative charge, or is it neutral? What do you think is going to happen?
Hold the comb near the paper.
Oh, all of something magical happens. It becomes attracted to a negative charge. Why? How is it possible to attract something neutral?
Hold the comb near the paper.
By using a charged object. You know everything is made up of atoms, right? You also know that the atoms are neutral, which means that within atoms, you will have equal number of positive and negative charges. So when you're using a negatively charged rod, what happens to the negative charges inside the atom? They will become repelled into the surface. What happens to the opposite charges? They will be pulled up to the surface. So which means that the surface is going to become polar. All right, those of you guys, some of you guys were arguing water is naturally polar, which means that you have water molecules, water is neutral, you got water molecules, one end of the molecule is going to be slightly negatively charged, the other end is slightly positive charged. So what happens to the molecules? They rotate, they spin around. All right, the molecules that carry the opposite charge is going to be closer to the negatively charged cone. All right, and neutral surfaces also will become polarized. Examples of it is if you get a negatively charged balloon and bring it near a wall, it's going to become attracted to a wall because the wall becomes polarized. Plastic is negatively charged by design.
Cherry filler is matte, like cling wrap, flat unrolls smooth and easy, and clings tight when
Glass it's an insulator, right? It becomes polarized. Porcelain becomes polarized.
you need it to.
Of course, you got problems with metal pods. Metal's like a conductor, so it's going to take the negative charges from
Comes out easy.
plastic and transfer them to the ground.
Yep.
And clean straight.
Polarization, polarization, polarization. Remember I said the Earth is slightly negatively charged? So what happens to Earth? Earth becomes positively charged through polarization. So after the charges become separated inside the clouds, and when the clouds become polarized for some reasons that we still don't understand, when the bottom of the clouds become negatively charged, the surface of the Earth becomes positively charged through polarization. So this brings us to the next question. Negatively charged comb is going to be able to attract pieces of paper. And the paper is neutral, which means that it's going to have equal number of positive and negative charges. Given the fact that the paper has equal number of positive and negative charges, how does a negatively charged comb able to attract paper? I'm going to give you 20 points for the best explanation. All right, I'm going to give you 3 more seconds. 3 more seconds to think about it. Okay, I'm not getting an explanation, so let me just elaborate. Like charges repel, right? And the unlike charges attract. Why is it that the force of attraction larger than the force of repulsion? That's what I'm asking. I mean, given the fact that the paper has equal number of positive and negative charges, why should the force of attraction be larger than the force of repulsion?
It's closer, right? Because
okay, so Nathan is making a good point. Nathan says because the opposite charges are closer, right? So which means that can we make the assumption that the electrostatic force is going to depend on the distance? closer the charges are, the stronger the force is going to become. Right? Immediately you make that assumption. Immediately you go, wait a minute, or else you would not be able to track paper. Nathan, I'm going to give you 10 points for that one. The guy who actually made that connection first was this guy. His name is Washington. You will be able to see his picture on the dollar bill. So notice that a lot of the forefathers, the people who actually put together the Constitution, fighting for it, for independence, were physicists, right? Is this guy Washington? Yes or no?
No.
Did you go there? Yeah, it kind of looks like Washington, but he's not. All right, evidently that was the tradition of the day. This guy who looks like Washington was Coulomb. So Coulomb is the guy who came up with the electrostatic force, the idea of the electrostatic force. And then he came up with this formula for the electrostatic force. So this is something that we need to discuss. It's known as the electrostatic force formula. Okay, guys, I uploaded this during the breaks. If you want to find it, just find it. If you didn't find it, that's fine. I'm gonna just set up the concept regarding this. All right, so Coulomb's law of the electrostatic force. This concept is very similar to the law of gravity that Newton came up with. All right, so let's just go over the law of gravity, the stuff that you guys are used to from physics 1. So Newton is the guy who came up with this. He realized that whatever this force is generated by the masses itself. All right, so you got the small mass, you got the big mass. So the product of these masses is, the force is going to be proportional to the product of the masses, which means that bigger the multiplication is, the bigger the force is. He also discovered that with distance, the force is going to diminish. All right, so R represents the radial distance between the forces measured with respect to the center of mass. So larger the separation distance is, smaller the force is going to be. All right, so the force diminishes as the square of the distance. So you increase, okay, boom. So you increase the distance, the force is going to diminish. All right, so the force is going to diminish as the square of the distance. That's it. Capital G that you're looking at is going to give us the strength of gravity. Ooh. All right, so this will be the strength of gravity. Gravity that you're looking at, this is the strength of gravity. It's extremely, extremely, extremely small. Okay, so evidently I don't have it here, so let me write it down. Strength of gravity, capital G, the universal gravitational constant, is 6.67 times 10 to the minus 11. It's going to be expressed in terms of Newton meter squared per kilogram squared. That's it. All right, so here's the strength of gravity. Strength of gravity being 10 to the minus 11. Okay, is this a big force or a small force? 10 to the minus 11 is going to make it extremely small, which means that gravity is going to be extremely weak. All right, so Newton originally came up with this. So what did Coulomb do? Well, he comes up, he uses the same formula, except the mass becomes the net charge. All right, so you got two net charges, Q1 and Q2. R is the separation distance, which is going to be squared. So that's going to give you the electrostatic force. K is going to give you the strength of the electrostatic force, which is known as the electrostatic constant, which happens to be a really, really big number. All right, 10 to the $9. If you had that much money in your bank, how much money would that be?
$1 billion?
It would be $1 billion, guys. Okay, give yourself 2 points for that one. All right, so the strength of the electrostatic force is about $1 billion. And the strength of the gravitational force is 10 to the minus 11. It's almost 10 trillionth. That's really, really small. All right, so gravity is extremely weak. Electrostatic force is extremely strong. Okay, so I'm going to ask you a dumb little question. The question is this. The formulas, why did they look the same? Why did they look alike? Any ideas? This formula looks exactly like Newton's formula, looks exactly like the Coulomb's formula. Why do these formulas look so much alike? Any ideas?
Is it because they are the same? They're just in like different units?
Okay, they do. Okay, so you can make that argument. I'm going to give you 2 points. Both of them are known as the inverse square laws, obviously. The Coulomb ended up doing something that you're not supposed to do today. It's called plagiarism. Okay, which means who came up with this formula? Who came up with?
Newton.
Newton is the guy originally came up with this formula. About a generation later, obviously Coulomb comes up with something that looks the same. Okay, the reason why we consider this plagiarism is because of the simple reason that you can make the assumption, guys, just get it into your head. Conceptually, you can make the assumption that the force is going to diminish with distance. There's nothing wrong with it. You can pull that out of your ass, and then you can make it stick, and it's going to stick just about anywhere, including the toilet paper. All right, you can make that assumption, and then you can say, hey, I just came up with it myself. I was just staring at the wall. I noticed that the force is going to diminish with distance, and that's it. You can make that argument. Here's the argument that you cannot make on your own. You cannot say under any circumstances that the force is going to diminish as the square of the distance. This is when you start to get into trouble, because this is not common sense at this point. You have to kind of justify that. But because he was using the force diminishing with distance inversely as the square of the distance, he should have given credit to Newton, which he did not.